Now we move to really the final chapter, the final set of discussions on in this course actually. So we're gonna talk about in this set of discussions about the basic limit theorems and the different kind of inequalities. So we will start with proving some of the inequality that will help us to kind of prove what you call the weak law of large numbers actually. Okay. So let's just start with Markov inequality. These inequalities are basic and important inequalities, okay, which kind of give you the bounds on the probabilities actually. So here the Markov inequality. So it says that if x is a non-negative random variable, so if x is a non-negative random variable, it takes only non-negative values, then for any positive value, probability that x will go beyond this positive value, so as x is non-negative, then what is the probability that x will take a value that is beyond what do you call this positive value a? These chances should be no more than the expectation of x divided by a. Okay? So in other words, these chances can be at most this number. So the probability that the x will take a value that is greater than or equal to any positive number, a given positive number, is this probability is at most expectation of x given by a, and we will see some of the application of it as well. So and let's compute, for example, the expectation of x. So by definition, expectation of x is an integral, say from minus infinity to infinity, x multiplied by the PDF of x dx. Okay? Now I can do what? I can distribute this integral into say two parts. So one part is minus 8 to infinity x fx of x dx plus what do we call a to infinity x fx of x dx. So in other words, I can break this into two integrals, so minus a to infinity and a to infinity. Okay, this is what is going to be the case. Now, since x is a non-negative number, then this product is non-negative. So since x is a random variable, a non-negative random variable that takes non-negative values, then x is one of the value of it actually. Okay. So x is a non-negative number and the PDF is a non-negative number, so this integrand is a non-negative number. And if this integrand is a non-negative number, this integral is a non-negative number. In other words, that this integral is a non-negative number. It's a number that is greater than or equal to 0. Okay? It's a number that is greater than or equal to 0. Now, in this term, if I drop this term, I'm going to say that the expectation of x is bigger than or equal to the sum that goes from say a to positive infinity x fx of x dx. Okay, x fx of x dx. You can also prove this in a similar way, you know, in discrete time case actually. So it's not a big deal. The only difference would be that instead of integral, you're going to have a sum actually. So why this expectation is bigger than or equal to x? Because expectation is sum of these two terms, and both terms are non-negative. So if you out of these two terms drop one term, this sum is bigger than or equal to the, you know, what do you call one term. Or you can say that this sum is bigger than or equal to, for example, one of the term, because both terms are non-negative. Okay? I'm using the fact this that, okay, if A and B both are non-negative, then A plus B must be bigger than or equal to A. Even A plus B must be also bigger than or equal to B actually. Okay, so if you drop one term, you know it should be bigger than or equal to one term. So this sum is bigger than or equal to this single term actually. Now, since I can say that x is bigger than or equal to, in this interval, x is bigger than or equal to A, so I can say that x times fx of x is bigger than or equal to A times of fx of x for all x. Okay, this is true in general, and if this is the case, then this integral that goes from A to infinity and A to infinity is bigger than or equal to A. In other words, that as x is bigger than or equal to A in this interval, so this integral x fx of x is bigger than or equal to A fx of x actually, and dx obviously. Dx. Okay, so hence I can say that the expectation of x is bigger than or equal to this, and this is bigger than or equal to this. In this integral I can take this A out, so you're going to have A to infinity fx of x and dx. Now what is this guy? I mean, if you wish, this is really equal to A times probability that x is bigger than or equal to A. So the probability that x is bigger than or equal to A is really, what do you call this probability? And what we have shown that this shows that the expectation of x is bigger than or equal to A times the probability of x bigger than or equal to A. If you divide by A, you're going to get this is bigger than or equal to the probability bigger than or equal to A actually. So this is really a simple proof in the case when x is a continuous random variable. You can precisely on the same lines you can prove what do you call the directly as well. Okay, directly as well. I mean, okay. Book gives. So I mean, if you see the lecture notes, they give you kind of another interesting direct proof, which is true in general actually. So another proof, maybe a short proof of this is that, okay, consider the indicator function, that indicator function of the set x bigger than or equal to A. Okay? So in other words, I is 1 if x is bigger than or equal to A, and it's 0 otherwise. Okay, so that's what I'm talking about. Now, as x is bigger than or equal to A, then x over A is bigger than or equal to what you call 1. Now, I only takes values 1 or 0. So if it take value 1, I can say that x over A, in other words, I can say that this implies that x over A is bigger than or equal to I always. Why? Because for I, you have two options. If it is 1, this is true. If it is 0, this is still true. Why? Because x is bigger than or equal to A. Okay? So since x is bigger than or equal to A, okay, so you can say that x over A is bigger than or equal to I. So if you take the expectation on the both sides of this inequality, expectation of A over the expectation of indicator function, now the indicator function is the indicator function of, what do you call, what would be the expectation of indicator function? The expectation of indicator function is going to be 1 multiplied by the probability of x bigger than or equal to A plus 0 multiplied by the probability of the same but complement. Okay? plus 0 multiplied by the 0 times the probability of the same but complement actually. Okay. Now this will go away, become 0. Expectation of x over a, 1 over a is like a constant, so you can pull this out. You can say that this is same as expectation of a bigger than or equal to the probability that x bigger than or equal to a. So this is a general proof in which we don't have any assumption on x that whether it is continuous or discrete. You can prove it in both cases actually. Okay. So that's a Markov inequality, which tells you that if you have a non-negative random variable, then probability that it is going to take a value that is bigger than a positive number, this probability is at most this number, expectation of x divided by, factored by, normalized by a. Okay. Now using this inequality, we'll prove another interesting inequality is called the Chebyshev inequality. Chebyshev inequality. Okay. So let's prove another inequality which is called Chebyshev's inequality. Okay. The trouble about the Markov inequality is that it is true only for what you call non-negative random variable. But now this proposition is about that x is any random variable. So if x is some random variable with mean mu and variance sigma square. Okay, so you have any random variable with mean mu and sigma square, then for any, so there is no restriction here, it could be positive, could be negative. For any k positive, okay, probability that x will deviate from its mean, in other words mu, at least by k, okay, in other words probability that x will deviate from its mean at least by number k, this is less than or equal to, in other words this probability is less than or equal to variance of x divided by k square, in other words the sigma square by k square. Okay, sigma square by k square. This is what that you can get. So let's see that how to prove. So what does Chebyshev inequality is telling you? That if you have a random variable with mean mu and variance sigma square, then probability that that random variable will deviate from its mean at least by number k, okay, is this probability can be estimated, or it has an upper bound sigma square over k. So this probability should not go beyond this number. The proof is pretty much simple. It's based on, what do you call, based on the, what do you call, Markov inequality. So here's a proof. So the probability that x minus mu bigger than or equal to k is same as the probability that x minus mu square is bigger than or equal to k square. In other words, if x minus mu is bigger than or equal to k, then x minus mu square is also bigger than or equal to k square. And if x minus mu square is bigger than or equal to k square, taking a square root will give you x minus mu equal to bigger than or equal to k. In other words, these two inequalities are equivalent. Okay, they are equivalent. So if they are equivalent, their probabilities must be same as well. In other words, those omegas which satisfy this inequality would also satisfy this inequality. And those omegas from the sample space which satisfy this inequality would also satisfy this inequality. So therefore their probabilities must be same. Okay, the set of omegas that satisfy this inequality must be equal to the set of omegas that satisfy this inequality. So therefore their probabilities must be same actually. Okay, this is what is the interesting thing. Now, if I take this random variable as y, okay, x minus mu square, I know this is non-negative. This is non-negative. So if I take this inequality y and I put say k square equal to say a, then the above inequality will become probability that y is bigger than or equal to a, where y is a non-negative random variable and a is a positive number. Then I know by Markov inequality this is less than or equal to expectation of y divided by a, which is same as expectation of x minus mu square divided by k square. Okay, and expectation of x minus mu square is what? This is what the precise definition of sigma square is, sigma square by k square. So this shows that this probability can be at most this number sigma square by k square. Okay. Let's do one example based on it. Let's do one example. Based on it. So here is one example in which we have to kind of apply the Chebyshev inequality. So you can see that it is of some use. This example is example 2a. So the example says that suppose that suppose that x represents that number of, so imagine you have a company, okay, that produces some items. Okay, I have a company that produces some items. So x represents the number of items that company produces in a week. Produces in a week actually. Okay, and it is known the average number of items that company produces in a week is 50. Okay, so let's assume that this average is 50. So the question is, what is probability? So first, what is probability that the number of items produced in a week is going to be bigger than or equal to 75? Okay. So what is the probability that the number of items that are produced is going to be bigger than or equal to y? So we need to compute this probability. Or what can be said about this probability? In other words, can we have an estimate of this probability, that what would be the estimate on this probability? Okay, this is the first part. The second part is that if we know that the variance of the number of items that company produces is 25, in other words that it produces the items between 50 plus 25 and 50 minus 25 on average. Okay, is 25. Then what can be said about the probability that week production will be between 40 and 60? Okay, so what is the probability? What is the probability? So in other words, what can be said about the probability that the week's production between in a week is going to be between 50 and 60. That week's production will be between 40 and 60, sorry. 40 and 60. Okay. So in other words, we need to have an estimate for this, and we need to have an estimate for this actually. So the first is really easy to estimate. So I can apply what you call the Markov inequality. So the probability that X, the number of items that are produced in a week, is going to be less than or equal to the expectation of X divided by the 75. And 75 is really 50 by 75. So, you know, this probability is less than or at most it's going to be 2 over 3. So there is, you know, this probability can be at most 2/3. So it can't be more than 2/3. It could be less than 2/3. So the probability that X is going to be bigger than or equal to 75, number of items that are produced in a week is going to be bigger than or equal to 75, can be at most 2/3. Okay? So the more you go away from, you know, average, the less likely the event is going to be. Okay? So that's the part A. How about the part B? So for example, I need to compute this probability. Okay? So if I say that the probability that X is between 40 and say 50, okay, this is what I want to have a similar kind of estimate for this probability. Okay, then what can be said? 50 and 60, sorry. 50 and 60. I want to turn this probability into something like this, actually. Into something like this. So the trick that could be, so in order to turn it into something like this, first you need to subtract, for example, mean. So let's subtract mean actually. So the mean is 50. So if you subtract 50 throughout this inequality, you're going to get 10, okay, less than or equal to X minus 50, less than or equal to what do you call 10. Aha, this would be equal to, I can write this as probability that X minus 50 is less than or equal to 10. Okay, absolute of X minus 50 is going to be less than or equal to 10. But in order to apply the Chebyshev inequality, you need to turn it into greater than or equal to. So you can apply the complementation rule actually. I can apply the complementation rule and I can say that the probability that this is going to be the probability that 1 minus probability X minus 50 is bigger than or equal to 10. Okay. then I have an estimate about this probability. Okay, I have an estimate about this probability by Chebyshev inequality. Probability of X minus 50 bigger than or equal to, what do you call, 10 is less than or equal to variance actually. So the variance of this is 25 divided by, what do you call, K, which is 10 actually. So this number is really 2.5. And if you multiply both sides by minus and subtract 1, so it's going to be 1 minus probability of X minus 50 bigger than or equal to 10 is going to be 1 minus 2.5. No, this is variance divided by 100 actually. Okay. Sorry, it's going to be sigma square. So sigma square is 25 and I need to square this. That's what I was thinking actually, that why you are getting a number that is bigger than or equal to 1. So this is going to be 25 upon 100. So if it is 25 upon 100, it must be 0.25. So this means this must be bigger than or equal to 0.25 which is 0.75. So what does this shows? That the probability, okay, that the number of items will be produced between 40 and 60 is bigger than or equal to 75. So in other words, there are pretty much high chances that, keeping in view this average and this variance, there are very high chances that the number of items that will be produced by company is going to be between 40 to 60. So it's 0.75. It could be more than 0.75. Okay. But it's at least 7.75 actually. Okay. So at least it's 0.75. Okay. Here is another interesting little result that I would like to prove before moving on. It would be a corollary, a lemma actually. Which I'm going to use as well later on. So the proposition is that if the variance of x is 0, then probability that x is equal to its average is 1. Okay? Variance is telling you what? So it's pretty much intuitive. Variance is telling you that how much on average x will deviate from its mean. Now if this deviation is 0, then this should mean that there is a 100% chance that x is equal to its mean. It will not deviate from, x will be exactly equal to its mean with almost surely, what do you call it, even actually, almost surely, with one probability. So how to prove it? Now by, say, Chebyshev inequality, let's compute the probability that x minus mu is bigger than 1 over n. Okay? Let's compute x minus mu bigger than 1 over n. By definition, this probability is less than or equal to variance of x divided by 1 over n square, but the variance of x is 0, so this entire term is 0. So this probability is less than or equal to 0, but I know that probabilities are greater than or equal to 0 as well. So therefore, this probability that x will deviate from its mean by a tiny amount, 1 over n, you can choose n as much as bigger is 0. Chances that x will deviate from its mean by even this number. So it could be a really small number if you take n big actually. Okay? It has probability 0.